Good afternoon and welcome to ZEBx's Decarb Lunch, the last one of 2025. My name is Natalie Douglas and I'm the Program Manager for ZEBx at the Zero Emissions Innovation Center. Today's webinar on balancing whole life carbon in BC step code buildings will be covering a topic that's really been top of mind for many of us in this industry, looking to hit the top levels of the BC energy and zero carbon step codes, all while keeping cost and embodied carbon top of mind. During a time really of rampant uncertainty and misinformation and economic constraint, I'm really heartened by how thoughtful and nuanced and pragmatic the work that this team has done. It's really well timed. And before we get into the presentation, I'd like to share my gratitude for being able to join today from the unceded traditional territories of the Musqueam, Squamish, and Tsleil-Waututh Nations. I'd also like to thank the City of Vancouver and BC Hydro for their financial support that allows us to offer these continuing education accredited webinars completely at no cost to you. My colleague Victoria is now going to drop some details about those credits in the chat and how you can get them. Please use the chat to ask questions, add relevant resources or events, or provide comments for the presenters or for the benefit of the rest of the audience. I'll be drawing on a lot of that conversation and commentary in the chat to help guide the discussion at the end of the webinar. And my colleague now is going to launch a first poll that gives us a sense of who's actually in the room. That really helps us with planning things coming up for future webinars. And with that, I'm going to pass things over to this exquisite trio of speakers today. We have Ralph Wells, Community Climate and Energy Manager at UBC Campus and Community Planning, Hugh Nolan, Building Energy and Carbon Analyst at Reload Sustainable Design, and Martina Soderlund, Principal and Founder of Reload Sustainable Design. And over to you, Martina, to kick things off.
Thank you so much, Natalie, for the introduction, and thanks everyone for joining our webinar. When Ralph reached out to us with the prospect of doing a study, we got so excited because we had done smaller versions of this work on our projects, probably like many of you, and we had wanted for some time to really build on those findings and in a more comprehensive study that we could also share more broadly to create some discussion in the industry. So what we had to come across was an increased need to really understand the balance point of thermal performance, step code, and embodied carbon. And we had found opportunities on our projects to reduce costs by testing scenarios holistically from the carbon lens. So that's what we're here to share with you, some nuggets from our findings in this study that is funded by UBC and their partners. So what we'll walk you through today, we'll take you through some background and context. We'll talk a bit about the study, the methods, and what we've looked at, and then we'll get you into lots of data and graphs to convey some key outcomes. And I really want to emphasize, it's really key outcomes here. We only have an hour together, and there's a lot of information and outcomes from this work. So try to hone it in on key messages. And we want to wrap up with a discussion around considerations for future code development. So with that, thanks again for joining us, and I will hand over the reins to Ralph Wells.
Thanks, Martina, and thanks, Natalie, for the introduction. And yeah, really, really exciting and happy to be here today for this presentation. I would just talk briefly a little bit about why we initiated this project, what the interest for us is. But in order for me to do that, I think I just have to even also briefly tell you a little bit about who we are, because we're in kind of a unique jurisdictional context here. And so the first thing is I like to talk about, we're not talking about UBC, the educational institution. We're talking about the city of UBC. We're talking about the small city that we're growing on our Vancouver campus. Up out in Point Grey. Some of you may have been out here and seen the city grow. We're currently around 17,000. I'll note just for scale that we will grow to over 35,000 people outside of the institution. Again, these are not students. Well, I'm sure many students live there, which is great, but it's not student res. This is just a residential community. Another issue, though, is that while we're growing this little city, we do not sit within any municipal boundaries in Metro Vancouver, and And so that leads to a few things. First, just noting we are an authority having jurisdiction for building code, and very pertinent to today, we've adopted Energy Step Code. We adopted Step 2 in 2018. And then lastly, I guess this is the key point, through a land use plan agreement we have with the province of BC, we've been given municipal authorities through MAVA, the same municipal enabling legislation that gives other cities their authorities. But it allows us to develop something called land use rules. So we can go a little bit beyond building code, for example. And that brings authority to our development handbook, but most importantly for today, it brings authority to something we call the UBC REAP. Yeah, and I'm not going to talk too much about REAP, but it's key for us. It's a comprehensive, the Residential Environmental Assessment Plan is really a comprehensive green building system that governs construction of the residential community. It's very holistic, though. It's LEED-like in terms of its comprehensiveness. We have a broad range of component areas here, ranging from biodiversity to climate adaptation, quality, health, and well-being, for example. And it is a regulatory tool, even though it looks LEED-like, and there's many preconditions as well as optional points that developers need to choose from to reach certain target thresholds. But I'm not going to talk anymore about REAP as much as I'd love to. I encourage you, if you're interested, just Google UBC REAP and you can learn lots more about it. But the key part I'll share with you is on the next slide. And yeah, so one is that as I mentioned, we adopted Energy Step Code in 2018, and June of 2024, we moved to Step 3 as our base code to stay ahead of the base code for the province. We also then in June 2025, just recently, we adopted Zero Carbon Step Code EL4 for all new residential construction on campus. And then here's the other key piece. Because we're able to, through REAP, we've also introduced a 10% embodied carbon reduction target. So all new construction will have to meet that target as well. And we're not stopping at 10%. That's where we're starting. Our climate action plan for the neighborhood commits us to a 40% reduction by 2030. And of course, UBC's climate action plan, like many jurisdictions, commits us to net zero by 2050. So even 40% is only a stopping point on the roadmap. So all of that to say is we're really interested in the question of understanding the relationship between Energy Step Code, Zero Carbon Step Code, and embodied carbon reduction. And then finally, I just want to acknowledge funding. Very excited and happy that we were able to receive an NRCan Codes Acceleration Fund grant in order to explore these questions and develop our energy, zero carbon, and embodied carbon roadmap. And as well, I want to acknowledge funding from BC Hydro, who are also very interested in understanding the relationship between energy efficiency, which is their core mandate, and embodied carbon. So that's the context. I'll hand it back over to Hugh, I believe, to take you through the fun stuff. Sorry, Martina, we're still there.
Yeah.
My apologies.
No worries. No. So yeah, so just to also put it into context to kind of the current cone landscape, also outside of UBC and the relevance of the study. So for those of you who've been around for some time in this space, it has been a very rapid evolution, I would say, of energy and carbon code adoption in BC since 2008, when we had our first ever energy code in BC, which was MNECB 1997. Lots have happened since that time. But one significant milestone, I would say, is in 2017 when the BC Energy Step Code came into place. And with that came the TEDI metrics, which is the thermal energy demand intensity, measuring the heat load on buildings. So what that did, it really put a much needed focus on the thermal envelope for improving energy efficiency. And this has had a significant impact on our local industry practices for the better. But what we're starting to see now on projects, as we layer in the higher steps of the BC Energy Step Code, Step 3, Step 4, the higher levels of the Zero Carbon Step Code, all electric projects, and embodied carbon, we're starting to reach a point of diminishing returns, particularly on the TEDI metrics. So what that means is we've found that aiming for low TEDI overall is starting to level out carbon impact if you look at it holistically, and it actually, in some cases, making it worse. So the implication of that is the risk of adding materials to our buildings that has limited benefit over the life of the building. So that's really kind of what understanding these balance points are, the focus of this project. Energy efficiency, embodied carbon, and capital cost are studied in silos. That's just a reality because they're difficult and complex to study, and they're done in separate tools and processes and softwares, making it more challenging. But how do we balance performance and practicality and not drive cost up on projects? We all know that the cost lens is what's driving decisions on projects. So to help study that, we have looked at two MURB archetypes, one 6-story wood frame mid-rise and one 36-story high-rise concrete tower. And the reason we picked these two typologies is that they are currently being built at UBC campus and is also part of their neighborhood plan development, looking into the future. And of course, we also see these typologies built in the marketplace elsewhere. I do want to mention that these are not phantom models for research. They are rooted in real-life projects and that were used as base case studies. So just to give you a bit of a study orientation before we get to the results, I do want to do a big shout out to the whole project teams that have supported this project. So in addition to UBC and ourselves at Reload, Ryder Architecture, Glotman Simpson, and Heatherbrae Builders have participated in the study and couldn't have done it without their input and support and help. So big shout out to them. And if I believe some of them are here today. If you are, feel free to say hi in the chat to let everyone know that you're here. I really appreciate your help. So the focus of this study is the thermal envelope. And the reason for that is that it's really the driver to achieve the higher steps of the BC Energy Step Code. Ventilation comes into play as well, but for MURBs particularly, it's really the envelope that's in the focus. So while we know that structure and concrete specifications have a big impact on embodied carbon, structure is not directly influencing TEDI or the Energy Step Code rating. So for that reason, we have not looked at structural options per se. It's really the focus of thermal envelope. We also wanted to see how combinations of the envelope performs under two fuel source scenarios. So one is the hot water district system that is fully fueled by natural gas at the moment, serving the UBC neighborhood. And the other is a low emission scenario with an all electric system scenario. So just to give you a bit of an example of the level of detail that we went into the study. So this is the archetype 6-story wood frame example and the options of exterior wall assemblies that we looked at. So in total, we looked at 12 options. They're grouped in 3 categories, top to bottom, and from left to right, they're ranging from R10 to R20 with thermal bridge effect taken into account, a full-scale thermal bridging. It was important to have the same thermal performance rating across the different categories so that we can compare options. But the first group here is looking at hybrid wall assembly with cavity insulation and different levels of exterior insulation ranging from 1 inch to 6 inches. The next group is looking at exterior only insulation. So what if we remove the cavity insulation? To achieve the same R values, we now have to look at thicker insulation, so ranging 4 inch to 8 inch exterior. And then the last group for the 6-story wood frame is what we call the alternative. So this is where we try to look at also swapping material options to more low carbon alternatives. One guiding principle we had on this project was we really wanted all solutions that we looked at to be viable, code compliant, and available in the local marketplace. So we have not studied any very innovative materials in this category for that reason. But just to point one example, we did swap mineral wool insulation to a wood fiber based insulation. For the archetype, the high-rise archetype, this is a summary of the wall options we looked at there, which is a combination of steel stud built-up wall with different levels of exterior insulation ranging 2-inch to 5-inch, with a window wall system with different levels of insulation in the spandrel. And we've run into a much higher degree of complexity, I would say, and options actually for the high rise compared to the mid rise when we're looking at material combinations and to achieve certain R values. And the reason for that is that the impact of thermal bridging for this archetype is much higher than the mid rise and really de-rates the impact of insulation. So no matter how much insulation you start packing on, it's really challenging to achieve higher thermal performance. But we were very interested in looking at material comparison for the window wall, comparing metal frame window wall to fiberglass. And we were also really interested, because of the high degree of thermal bridging, to look at the impact of isocorb, which is essentially a balcony thermal bridge system. And we hadn't looked at that ourselves before from an embodied carbon perspective. And we knew that it also would have an impact on the thermal insulation or thermal performance. So could that reduce both carbon and improve thermal performance is something we were really, really interested in. And just mention something about the extent of costing information. So again, we looked at thermal envelope packages only in the study, and we have compared the incremental cost difference between those. All the costs are provided by Heatherbrae Builders, and we did study the net present value analysis over a 20-year period. And just to get a sense of the overall impact of the thermal envelope have on the whole project compared to the whole project cost, for that, we worked with the Altus Group Canadian Cost Guide for a MURB in Vancouver. So that's a bit of study orientation. I'm now going to hand it over to Hugh to take us through the technicalities of the study.
Thanks, Martina. So for the study, we wanted to look at a parametric modeling approach, meaning we wanted to test every single iteration of these options against each other. So the climate zone was fixed to UBC Vancouver campus. We have the 2 archetypes. And for all of the envelope options, we tested all of the assemblies previously mentioned against each other, which resulted in 288 envelope combinations for the mid-rise and 192 for the high-rise. The embodied carbon impact of each of these envelope combinations was calculated, and each was simulated using a high emission and low emission scenario that were discussed as well, which made the total amount of cases studied to be 576 for the mid-rise and 386 for the high-rise. Each of these cases was then sorted out into their respective energy step code levels that they achieved, with all of the energy, carbon, and cost output metrics listed here to post-process. So as far as we know, there's no tool available to undertake this kind of parametric analysis for energy, cost, and carbon simultaneously. So here at Reload, we wanted to just start developing our own. As Martina mentioned, we had kind of started developing a while back, and then this is our first project that we really got to test it out on a bigger scale, which was really exciting. So we use Grasshopper to manage the energy simulations, the embodied carbon calculations, and the cost analysis in unison, pulling raw data from a series of different softwares that are all listed here. The results of which were then post-processed using a combination of Grasshopper itself, Excel, and Design Explorer. And Design Explorer is just a parallel coordinates tool, which makes it easy to see the relationship between the key output metrics. So trying to quickly and concisely summarize all of the data that we have. I'm just going to start a quick overview of the results and look at what we're going to talk about, and just a reminder of the main questions we wanted to study. So we're looking at carbon, the embodied and operational, for each of the archetypes. We want to see how the energy and zero carbon step codes will affect the whole life carbon. Then we'll do a little deeper dive into the assembly options and see how they compare against each other for the different archetypes, and really focusing on the embodied carbon versus the TEDI, the TEDI being what is driving the step code levels for the study. And then we're just going to do a quick review of the cost implications of all of the cases that we looked at. So just to, I suppose, open up with a quick example of what the parametric modeling approach kind of looks like, and what it yields in terms of results for them analysis. It helps to give us full spectrum of results for any of the key energy, carbon, and cost metrics that may inform design decisions, allowing us to see the relationship between the outputs and in turn try find an optimal balance point. So just for an example here, I've shown the mid-rise results, and we can see that the majority of combinations meet step 3, but let's just say you're in a jurisdiction that is required to meet step 4, and you want to try to achieve a minimum whole building LCA from that. We can see if we filter to those 2 options, there are still countless cases that perform very similarly, but greatly impacting their present value. So just in general, it's a very useful tool for leaving no stone unturned. I suppose it also just puts into perspective that there's no one perfect combination or formula for any of these answers. It's rather finding an optimal balance point depending on what key design options are most important to you. So to focus back in on the study, here we're just going to have a quick overview of the embodied carbon breakdown for both the mid-rise on the left and the high-rise on the right. The ranges represent all of the cases that we've looked at, so all the different combinations. And we can see for both archetypes that the embodied carbon is pretty dominated by the structure and parkade, neither of which we actually analysed within this study. So, but you also definitely can't ignore it if you're trying to reduce your carbon footprint. So for the study, we did look at the envelope only, as that's what's affecting the thermal performance and in turn the operational emissions. For the mid-rise, the envelope accounted for between 26 and 36% of the whole building carbon, whereas for the high-rise, it only accounted for about 11 to 18%, as the archetype is a high-rise concrete tower, so it's been dominated by that structure. In terms of energy impact from the study, we focus on the thermal envelope as it's what's mostly affecting the heating portion of the total energy. The low emission scenarios at the top here, we can see that the space heating is accounting for roughly 10 to 15% for both archetypes, give or take. For the high-rise emission scenarios, however, it's closer to around a quarter of the total energy. That jump in scale is a result of using a heat pump system for the all-electric low emission options with a COP. Whereas for the for the high emission scenarios, it's natural gas, so there's no COP. The domestic hot water for both scenarios was assumed to have a COP of 1. So the energy will not be affected by the study. However, the fuel switch to natural gas for the high emission scenario would have a great impact on the operational carbon in terms of domestic hot water. So just try to put that impact into perspective. We have the rapidly increasing difference between the high emission and low emission scenarios for the study over the 6-year period that we looked at. So the y-axis shows the cumulative emissions per kilowatt hour of energy, and the x-axis is the 6-year timeline year by year. So I suppose in reality, we would hope that the high emission scenario should start to plateau over time as the grid is supposed to decarbonize. But for this study, we just assumed it remained consistent throughout the 60 years, with the idea, I suppose, that if it were to decarbonize, it would fall somewhere between the range of these 2 scenarios. So here we're just going to have a high-level review of what impact the BC Energy Step Code levels can have on a whole life carbon emission, as well as the zero carbon step code. So to start, we have the percentage of high-rise on the top and mid-rise on the bottom, the percentage of cases that were studied and how they fell into the different buckets of step 2, step 3, or step 4. For both archetypes, the majority of envelope combinations resulted in achieving step 3, demonstrating that only the highest thermal performance cases were enough to meet step 4. Only the high-rise had cases that met step 2, all of which had large window areas and poor opaque wall performances. I suppose in UBC, we don't really see any residential high-rises with a wall-to-window ratio greater than 50%, which was the maximum studied. However, within a more general market context outside of UBC, it's not that uncommon to have higher glazing areas, which would likely result in an increase in step 2 options. To try to capture what the steps mean from a whole life carbon perspective, we've taken the lowest calculated embodied carbon for the lowest step achieved. So for that would be step 2 for the mid-rise on the top left and step 3 for the mid-rise on the bottom left. And we're also looking at the highest embodied carbon scenario for the step 4 cases for each archetype. The operational carbon shown here is for the high emission scenario over the full 60-year period that was studied, which is clearly dictating the whole life carbon emissions. In both archetypes, the higher step code levels driven by that TEDI metric results in big carbon reductions from a whole building LCA. However, if we take the exact same cases and switch to the low emission scenario, the relationship between embodied carbon and operational carbon completely flips. So the absolute value of the embodied carbon in the gray here remains the same between the large and small donuts. However, now it makes up about 80% of the total emissions from a whole building LCA. In this instance, so in this instance, the lower steps have a slightly lower whole building LCA results, but the difference is pretty marginal. So if we look at a combination of how it's all looking for both scenarios, it's worth noting that the best and worst cases are used here to really try to capture that full spectrum. In both mid-rise and high-rise, there are many step 4 cases that achieve a lower embodied carbon than step 2 or 3 counterparts. The low emission scenario just really helps unlock that freedom to focus more on material choice and quantity to optimize your whole building LCA. So to emphasize that point, we're now going to look at some mid-range step 3 options from the high-rise. The table on the right just highlights what the layered choices of that opaque wall option were that Martina previously discussed, mainly being a variation of window wall frame material, insulation thickness, and the balcony thermal bridge mitigation using isocorb. The graph shows the embodied carbon impact of the building envelope only, so excluding any of the structure or parquet that was previously shown. And the secondary axis is the operational emissions over the 60-year period for each case, using the low emission scenario. So as we can see, all the cases perform very similar in energy performance and operational emission. But the combination of assembly choice, wall-to-window ratio, and glazing performance greatly impacts the embodied carbon. So for the fiberglass frame window wall options, they're beneficial from both a carbon and energy perspective, allowing for a reduction in insulation materials to meet the same envelope thermal performance. The mitigation of the balcony thermal bridges does help to reduce the embodied carbon, but can be a costly decision. I suppose just in general, we can also see that the window wall frame material and window area are what are driving the carbon for the high-rise. So for this slide, we're going to dive a little deeper into what the impact of these envelope design decisions can mean in terms of your energy step code and embodied carbon. We're going to look at the mid-rise here as an example, looking at the embodied carbon impact on the left and the TEDI on the right. For the highest thermal performance studied for mid-rise archetype, which would be comprised of a 20% wall-to-window ratio, or 20 for the walls, triple glazed windows, or 40 for the roof, and or 20 for the floor. We just took the mineral wool here, but it's the same thermal performance as the spray foam. And this combination would result in 41 kilograms CO2e per square meter of the built floor area for all of these measures combined, which is, again, it's the embodied carbon impact of the envelope only, excluding structure and parquet. This envelope combination would result in a TEDI of around 12.9 kilowatt hours per meter squared, which would be a step 4. Just a reminder, the step 4 threshold is 15 kilowatt hours per meter squared, and is indicated by the grey dashed line here on the right. So we're going to look at the relative impact of individually changing these envelope options to its lowest performing counterpart, while keeping the rest of the envelope as a high performance. So for example, if we change the wall-to-window ratio from 20% to 40%, there's a pretty significant increase in both embodied carbon and TEDI, indicating that smaller window areas are beneficial from an energy and carbon perspective. But again, it's worth kind of zooming back out and reminding ourselves that we're only looking at a small portion of the total embodied carbon, so it's not massively tipping the scales from an embodied carbon perspective. If we revert back to 20% wall-to-window ratio and instead reduce the thermal performance of the wall to R10, we can see there is still an increase in TEDI, which is still pretty significant, but it's less impactful than changing the window size. From an embodied carbon perspective, it's actually beneficial this time. So with less insulation material, meaning that there's a 10% reduction on the envelope carbon. Reducing from triple to double glazing has the same effect, reducing the carbon by 5%, but increasing carbon TEDI by 12. And if you were to keep everything else robust for this specific case, the switch from triple to double glazing would still meet step 4, which was interesting. Reducing the insulation thickness for the roof didn't have much of an influence on the embodied carbon or TEDI, just kind of because of the geometry of the archetype. And the floor options had the same thermal performance, so there's no difference in TEDI, but the material switch from mineral wool to the spray insulation helped minimally reduce the embodied carbon and is also a cheaper option. So it's a bit of a win-win. So yeah, if we're going to try connect the relationship between TEDI and carbon on a whole life scale, we can really start to see the importance of the lower operational emissions. So on the scatter plot here, the y-axis is the TEDI output for all of the cases that were assessed, with the combined embodied and operational carbon over the 60-year study period shown on the x-axis. The cluster on the left are all of the low emission scenarios, and on the right are all the high emission scenarios. And it's worth kind of just remembering back to the donut slide that the embodied carbon for these two clusters are the same. Really depend on the case. It can be approximately about 140 kilograms CO2e per square meter here. So the sheer scale difference between the whole life carbon of these clusters is due to the operational emissions. The high emission whole life carbon is about 4 to 5 times greater than the low emission counterparts, and no amount of material optimization is going to compensate for that gap. So it's really important to try push for those higher versions of the zero carbon step code. Just to try put a bit of perspective into the scatter plots here for everyone wondering what's going on. The color legend represents the wall R values, and even at this level, we can try to pick out some trends. So, for example, the 3 groupings of lines in the high emission scenarios on the right, they're the 3 different wall to window ratios that were tested, with the 30% wall to window ratio being the furthest to the left. Yeah, within those clusters, we can see that the yellow dots of the R20s are all at the bottom with the lowest TEDIs. And for the high emission scenarios, it's also the most beneficial. If you really want to start squinting, you can probably start seeing double versus triple glaze. But if anyone has any time to really start picking through, you can read it in the report or even just chat to me. I've looked at them many, many times. So I suppose zooming back out, there's very clear, strong correlation between TEDI and whole life carbon from the high emission scenarios, meaning thermal performance is by far the biggest driver and is vital for mitigating emissions. Therefore, meeting any of the higher steps of the energy step code is crucial for lowering your whole life carbon. However, for the low emission scenario, there is no real strong correlation between TEDI and the whole life carbon. Like that is to say, thermal performance is still important from an energy perspective, but there is more room for material optimization to realize the most amount of savings from a whole life perspective. I suppose it's also worth pointing to the step 4 dots in the low emission scenario here on the left. There are plenty of options that are achieving a lower whole life carbon than a lot of the step 2 or they're all step 3, a lot of the step 3 cases above, which just kind of redirects the point we're trying to make earlier that a higher step doesn't automatically mean higher carbon. It really is depending on how you're designing it. If we move to costing now, we're going to start by looking at the mid-rise first. With the different assembly options listed on the x-axis here, starting with the 3 buckets of wall assemblies that we looked at, which are the cavity and outboard insulation, the outboard only, and the low carbon alternatives. Each of those have their R10 to R20 terminal values. Then we look at the roof, floor, and then finally the glazing. The bars are following the left axis and showing the embodied carbon per square meter of the respective assembly, and the dots are the cost per square meter of the respective assembly and follow the scale on the right. The embodied carbon values also are cradle to grave, excluding operational here, just to try capture the impact of replacements that are required during that 60-year study period. However, the costs are only the present value, as the NPV study was for 20 years, and we didn't look into maintenance or replacements for the costing. So for the wall, the roof and floor options studied, trends are pretty intuitive. An increase in thermal performance means an increase in material volume, means an increase in embodied carbon and cost. However, for the windows, double glazing is cheaper than the wall assemblies that are below R16, and triple is cheaper than anything above R16, making it a cost-effective option in certain cases. However, both glazing options are about double the carbon impact of the wall assemblies when taking into account a replacement that's likely going to be needed during a 60-year study period. A reminder that all the mid-raise options we looked at were achieving step 3 minimum. Again, just to kind of touch on that there is room for design optimization to save on cost and carbon while not greatly affecting the overall operational costs. So the cost and carbon breakdown for the high-rise is a little bit more nuanced due to the layered thermal performance from either the metal or fiberglass windows on the window wall system or from the balcony thermal bridge mitigation that we both touched upon. The summary of how that breaks down per option is on the x-axis here. And similar to the last graph, the bars represent the embodied carbon and the dots represent the cost. However, as it's so dependent on all the other elements for the walls, the cost in carbon are per square meter of the total envelope. So we're including in here the glazing, which we set to double glazed for this graph. The roof is set to R30 and the floor is the mineral wool. So if we just kind of focus in on the likes of options 4 or 5 here, we can see that despite the fiberglass being a more expensive metal frame, more expensive than metal frame when comparing individually, the increased insulation thickness required for the metal frame to meet the same envelope thermal performance helps to offset that cost premium of the fiberglass, while also helping to greatly reduce the embodied carbon of the envelope. The Core balcony thermal bridge mitigation does help with the overall thermal performance, but is a more costly option. I would say in practice, it would be more beneficial to try minimize instances where the balcony is penetrating the envelope. Just full stop. Just try optimize your balcony design. The trends ring true when you reduce the wall to window ratio to 30%. It also helps reduce costs and carbon. While it's uncommon to see window wall assemblies that are only 30% wall to window ratio, it does indicate that it is more environmentally and economically beneficial to try optimize your window design and not go over the top with massive glazing areas. I suppose to wrap up the results section, I'm just going to zoom back out on a macro scale and look at how the respective energy set code levels for the high-rise options studied perform from a net present value perspective. So again, the net present value is the capital costs of all the envelope measures, as well as the annual operation costs over the 20-year period. We have the high emission scenarios on the left and the low emission on the right. Again, we're not accounting for any maintenance or replacement here, and we're also excluding the massive costs of all of the other project parts. So there are more layers, I suppose, as we're pointing out. There's more layers for the annual cost of each scenario, such as like fixed annual connection fees and stuff, which may differ from study to study or depending where your building's located. But we do believe that the annual saving benefits from an all-electric heat pump system would remain compared to a direct natural gas system. In either emission scenario, the annual savings from higher step code levels generally yield a lower MPV, meaning if you do have the capital investment available, it is more beneficial in the long run to invest in a more robust envelope and aim for that higher step. It's also worth remembering that the envelope is only a small proportion of the overall construction costs, and it's unlikely to massively increase project budget overall. If you focus in on the step 3 options here, we can see that they have quite wide whiskers to indicate there are more specific envelope combinations that can maximize your MPV savings. For the low emission scenario, relaxing that absolute TEDI target of 15 might allow for more cost-effective solutions while not hugely affecting the whole of carbon. Like you could have anywhere like 15, 16, 17, 18 kilowatt hours per meter squared. If you look at a total building operation for the COP, that's not hugely increasing your operational costs. So that is a quick run through of the results. I'll just pass it back to Martina.
All right, so we're just going to wrap up here with a few summary of the findings and some considerations to bring us into the discussion section. So just to zoom out for a minute from all the details and the numbers, just wanted to recap on some of the bigger picture finds from the study. So compared to overall average construction costs for these MURB archetypes, the thermal envelope accounts for 8 to 15% of overall construction cost. For embodied carbon, the same thermal envelope accounts for 11 to 36% of the total embodied carbon when you consider envelope and structure. I do want to point out that these ranges are not the step from going from step 2 to step 4. This is the range to capture all the scenarios that we looked at, which is a mix of step 2s and step 4s in there. And the higher range of the embodied carbon here, the 36% range, is for the mid-rise, where we saw that the thermal envelope has a bigger piece of the embodied carbon pie than the high-rise due to the concrete structure that has a bigger impact on the high-rise. We found that there are step 4 thermal envelope solutions that are more cost-effective than both step 2 and step 3. And similarly, we found that there are step 4 envelope solutions that have lower carbon versus step 2 and step 3. One of the big takeaways that we found in this balance point between step codes, zero carbon step codes, and long-term whole life carbon is that with a high emission fuel scenario, so the gas-based fuel scenario for heating, energy step code 4 with the TEDI really matters for the building whole life carbon. It has envelope has a really big impact for the whole life carbon over time. But for the low emission fuel scenario, the all electric TEDI is no longer the driver for whole life carbon. And the balance is now swayed towards more focus on the materiality than the thermal performance. So what does this all mean? And kind of bringing it back to the code aspects again that we talked about in the beginning. Some of our key findings recommendations from this is to not compromise on energy efficiency. So regardless of the fuel source, a low energy use intensity or a low energy consumption equals low energy cost, which of course is really important for affordability and equity and over the long term. Do not compromise on low operational carbon. So the higher levels of the zero carbon step code is really, really important in the mitigation of the climate change impact that the building sector has. Consider relaxing the TEDI target in the step code for EL4 buildings. And this is a really important point that we want to highlight, that while we really support the TEDI, having that absolute number of 15 is becoming a bit problematic when you're juggling all these aspects. And having flexibility on that when the operational carbon is low from the systems really leads to more flexibility in design option that can also lead to cost savings. Maintain step 4, the high level step code for EUI and TEDI for high emission scenario. The thermal envelope really matters when you have that as a fuel source. And yeah, lastly, as we think about the code landscape and where it's going, really like to put a pitch in there for the consideration of a whole life carbon compliance pathway in the future code, so that we can make more balanced decisions and provide more design flexibility on our projects. So with that, I'm going to hand it over back to Ralph for some final remarks before our discussion.
Thanks, Martina. Yeah, I'll be brief. There's just, just a couple of takeaways and thoughts. And what did I learn from the policymaker / regulator perspective? And that's the takeaway. Those are the takeaways I need to take from this. Well, first of all, I learned a lot. This has been extraordinarily useful. But one thing I just want to start with is a statement. And the statement is this: achieving the upper tiers of energy step code is not a zero-sum game with embodied carbon. I'm going to repeat that. Achieving the upper tiers of the energy step code is not a zero-sum game with embodied carbon, okay? And I'll break it down a little bit. Already the thermal elements of the envelope that drive thermal performance, a relatively small piece of the embodied body carbon pie. So you saw that. The other piece, of course, is the parts you change to improve thermal performance is only a piece of that smaller pie. So it's just not that big. And then finally, and most importantly, maybe though, it's design decisions are what drive really, not the step code jump, but the kind of design decisions you make when you're designing your envelope, right? The material use and design. And that bodes well because that thinking fits within a performance-based code framework. Okay, so that's a high level thinking about from the regulator's perspective. That means embodied carbon can slide into and fit into a performance-based code approach. The other key, just repeating what Martina's very clearly just laid out in the slide, but still saying it. If we have high emission fuel sources, TEDI, high performance TEDI targets are really, really important. You got to address the operational emittance, and the embodied carbon question just isn't really relevant. But the nuance is, yeah, it's very interesting to think when we switch to low carbon, if we're EL4 like we are here at UBC, really, there's opportunity, I think, to think about the highest TEDI targets relative to those highest TUI targets and what some flexibility might mean in terms of managing costs and creating opportunities for design. And I think that's just the key sort of high level I wanted to close with. Thank you.
Thanks so much, Ralph and Hugh and Martina. That was excellent. We have a request in the chat, Hugh, if you could go back to the past slide. I don't know if they want to dive into some of those things again or take a screenshot. I'm not sure. I will say, just for the purpose of the audience, we are going to be sharing these slides after, and this is being recorded and it will be published in the coming weeks. So don't be scared. It will be shared after this. You can take notes now, but you'll have an opportunity to dive into this content. Okay, moving into some of the questions that have come up in the chat. I think that one thing that came up a couple of times, Zara mentioned it. Martina, you've already answered it partially, but I do think that it's something that we can expand on, which is the limitations of this study. Maybe, from Zara's perspective in particular, it's the embodied carbon impact of mechanical systems and that fact not being integrated into the study. Obviously, this study could have way more different combinations and permutations, but any other reflections, Martina, on the fact that that was not integrated in the study, and if there's any highlights as to that impact and how dramatic it would influence this study if that had been integrated?
Yeah, sure. So I guess there's two important aspects that were not studied. So one is the embodied carbon on the mechanical system, which is one piece. And I think the question was if going from step 3 to step 4 would significantly increase embodied carbon of the system. So and the answer is no, not directly. And because the step 3 and the heating load range within step 3 in the step code going from TEDI 15 to 30 is really large. And you can have a really good step 3 project that is close to step 4 performance. You will not see any difference in system sizing, which is also speaks to the point of kind of the TEDI has been very powerful. We call it the TEDI revolution, but the challenge of TEDI is that it's based on a decimal point in the rating, which doesn't always lead to overall better outcome. The other aspect that's also not included in the study is structural options or structural efficiencies or concrete specs. So really focusing on the thermal envelope, but to reduce embodied carbon for the project, there's a lot that can be done in those considerations that would really reduce overall carbon significantly as well, other than the thermal envelope. I don't know if Ralph, you want to add anything to that question?
No, thanks, Martina.
No.
Sorry.
Great, Martina, thank you. Yeah, there's a couple of different things. I think Roberto brought up a little bit earlier about the impact of balconies. I think it's an important thing to talk about, in that a lot of folks have this perception that, maybe higher performance buildings don't have some of the livability aspects. And so, being able to hit these high targets, it's still being able to reduce embodied carbon and hit a high performance, good airtightness, all that. Maybe just posing the question, what are some of the tips for, I think Hugh, you spoke about it really briefly, but we can do this. Like we can still have like very livable buildings. We can have balconies, and we can build high performance buildings that are low embodied carbon. So maybe expand on that piece.
Yeah, I suppose like again, it kind of comes back to the high rise being so driven by so many other aspects of the envelope, not just the increase in insulation. It took us a lot of different iterations to try to get to that balance of that table that we looked at, and like comparable cases. Because yeah, we were finding like hacking out insulation and stuff. Really, we had hit a plateau. We couldn't achieve much higher R value than R9, and a big reason for that was because again, like we took the archetype as it was, and it had quite a high linear length of of balcony penetration, and I think we were both very tempted in the middle of it to just optimize what those balconies could be and try to have that as a solution. But instead we wanted to try to see how we could mitigate it. Because of that, like we're not to try to compromise on like balcony, not to try and minimize the amount of balcony or the livability of these high performances. But I think there definitely would be a point. Again, it's like there's no right answer. There is an optimal balance point somewhere that if you can minimize the incidences where balconies penetrate, or even just like see how much of it can be cantilevered, or like really like that could be a beneficial design decision from carbon and cost perspective. I think if you can really try optimize your balcony design rather than just having like full perimeter balconies with some semi not really usable space in them, and I think that's kind of more point that I was trying to make on that sense. Because yeah, I do think there is an optimal balance point there of not just stripping away balconies, and because they also have the knock-on effects of having like shading and everything. That there's many benefits to having them there. It's just to not do it excessively would be a point I'd be trying to make.
I don't know if Martina or Ralph, you want to add anything there? I think generally speaking, when we're talking about embodied carbon so often, the answer is not just material substitutions or not one silver bullet. It is thinking about it a little more holistically and seeing how the design can dramatically impact the wins that we can achieve, both from the cost perspective and the high performance perspective. I'd also like, before we get into maybe Teddy more specifically, because there definitely is some lively chat about that, I did want to highlight the comment about integrating resilience. So indoor temperature in case of loss, energy demand, future climate demands, when we want to choose that optimum scenario, trying to integrate how this all plays out in, also considering this resilience lens. I'm sure because you guys have dove in so deep on this topic, you might have some reflections. Martina, you're nodding your head quite a lot. I don't know if you have any reflections on that. Also, Ralph, as essentially a municipality, there's a massive priority across all municipalities in BC and from the province on adapting and building new buildings that are resilient to our future climate. So any reflections on that? How do we orient the findings from this study within that context?
Yeah, I'll say something first and I'll let Ralph speak. But yeah, I was just nodding and also kind of smiling a bit because yes, absolutely resiliency and the thermal performance from that aspect is so important. And I was just smiling because the buildings are also very complex, right? So, and that's the challenge. We have all these metrics and all these targets and requirements that we're trying to meet and trying to juggle. And in some cases, they might have some conflicting impacts on one another. So in some cases, we see that a reduction in SETI might be counterproductive to a TEDI. So there's a lot of fine tuning and balance points if you think about meeting these metrics that can be considered. So I think having a conversation around the priorities it will be really important. Like we can't look at these things in silos. There is no perfect answer. So how do we have a space for those multiple considerations, and where do we find those balance points? Over to you, Ralph.
Yeah, just really just thinking a bit about resiliency and especially focusing on sort of the overheating side of the equation. It's an area I've had a lot of look at. I think the first thing I say is all the work that I've been involved in, what we've done is sort of to remind people or let them know is that TEDI is really focusing on thermal focus for space heating. And so, if part of this conversation is about, well, a higher TEDI might help us, with overheating, it doesn't really. And in fact, it can have negative impacts if you're not careful. It's more thing. Although there's a sweet spot with glazing, right? In terms of heat gain from glazing and potential to reduce embodied carbon here. I think that it's a nuance, a detail thing to maybe bro in. But really, it's about things like external shading, and worrying about your solar heat gain. So that's back to glazing. That's going to drive resilience. And so to me, it's not as much a part of the TEDI. It is part of the overall TUI equation in terms of making it. And as you can reduce those, so there's some discussions. I'm a little distracted because I'm answering a question in the chat about MEP, mechanical equipment. So adding passive thermal elements to your envelope that are different than the ones that affect TEDI to prevent overheating can also very much help you reduce the size of your mechanical equipment. So it's kind of complex here, but it doesn't change the overall argument. I think it's just smart design and thinking about all of these elements in a holistic way is the key. I guess that's how I would answer it.
Yeah, thanks, Ralph. Again, it's very hard to be succinct with this type of work. It is nuanced. It does require discussion. But as we're closing up the hour, I did want maybe to give you a chance, Ralph, to respond about how maybe you're taking away some of these findings from this research, and you have to interact with UBC Properties Trust, and you guys are cost focused. You're an organization that obviously has exemplary goals for reducing emissions, high performance buildings, but you're also very cost focused. How do you think that this will help you? This work will help you tell that story maybe more clearly, and maybe focus folks' attention on the points that really matter, if that kind of directs you.
Yeah. No, first of all, maybe it's sort of a base case scenario because I really want to share with people, that we've already got to step 3 and EL4, and 10% embodied carbon with really strong consultation with UBC Properties Trust and our development community. So, and I just think it's a little bit outside of this discussion, but I think when you look at those life cycle costing numbers that we saw earlier, it's just a reminder when we're just talking, and it's this concern about regulatory costs that we're sort of hearing more and more about. That's getting profile right now. When we're talking about performance-based parts of the code and that smaller first step into embodied 10%, step code and performance-based moving away from prescriptive can be saving you money. It's a really smart design-driven approach, and I think we've already kind of made that case. Step 3 buildings can have lower life cycle costs than step 2 buildings because you got a lot of energy cost savings, for example. So I think the real conversation's in front of us. As we move from 10% embodied to 40, that's big and hard. And then we also have this conversation about what step 4 means. So again, I think we have a very cost-effective place that we're in right now. You should be proud of that, and I want to say that out loud as well. But yeah, so this is really helpful to think to the future. Unfortunately, we have a bit of time before we need to make those decisions or work within the context of the provincial requirements. So I didn't quite fully answer,
Awesome.
But
No, it's a hard question. It is the end of the hour, so I just want to start wrapping things up, and thank you all very much for sharing this information. Again, it's been stated in the chat, but this report is going to be published likely sometime in early 2026, likely January. We're going to share this recording and the slides after this webinar. I just threw in a link to a tour that's happening on Wednesday that we're hosting. It integrates embodied carbon, circularity, operational performance. And so if it is part 9 focused, but if you're very passionate about the topic, I think you'd probably enjoy attending that. All around, I really appreciate the leadership that UBC and Reload and the whole project team really has shown in essentially confronting this complex, overlapping harmonization of all these things that we talk about so often. This is a start. Obviously, there's more to do, but I even saw Scott from the province talking about how, they're working on a lot of how they can maybe adapt Teddy and, how we're constantly learning about how to build better buildings. So thanks so much for your leadership. Thank you all for attending today. And I hope you have a wonderful rest of your day and week.
Thank you so much.
Thank you.
Thanks, everyone.